So in the next few videos, I'm going to go over a few more miscellaneous topics regarding assembly programs, and I'm going to end with a full example and an introduction to the Mars simulator. So let's first talk about how large constant values are handled. So note that with MIPS instructions, there are certain formats that are allowed, and these formats do allow you to provide an immediate value as an operand, but the sizes of those immediate values are usually limited, right? So out of the 32-bit instruction, only 16 bits are kept aside to specify an immediate value. But what if I want to provide a 32-bit constant value? What if I want to load a register with a 32-bit constant value? How do I do that? Since I can only provide 16 bits of the immediate value in each instruction, I will need two instructions to kind of work together to load a 32-bit value into a register. Okay, so let me show how that's done. If this is the 32-bit value that I'm trying to load into a register, I break it up into two halves, A and B. Then I use a special LUI instruction, which stands for load upper immediate. What it does is it takes the first 16 bits as an operand, and it places this into the first 16 bits of a register. Right, so these are the most significant 16 bits, and this latter half are the least significant 16 bits. So load upper immediate takes that 16-bit operand and places it into the top half of a register. Then I do an OR immediate, and I place the result back into T0. One of the operands is going to be T0, and the other operand is a 16-bit constant, which would be the value of B. So essentially, I'm taking the current value in T0, which is A in the top half and a bunch of zeros over here. I'm ORing it with the 16-bit value B over here, which ends up placing the value of B into the second half, right? So finally, when this is done, this gets replaced with the resultant B. Okay, so it takes this combination of two instructions to place a large 32-bit constant into a register. I have to break up that 32-bit constant into two 16-bit constants, use load upper immediate to populate the first half of a register, and then OR that result to make sure that the second half then gets placed into that register. Okay, then there are a few other examples where we provide immediate values. One is, for example, a conditional branch, where I might be doing branch unequal to $S0, $T0, and then the location I need to jump to in case these two registers are equal. And again, the MIPS instruction format lets this only be a 16-bit constant value, right? So this means that I can only jump to a location that is not too far from my current program counter, right? So essentially, this 16-bit value gets added to my current program counter value. So I can only jump, up or down by a displacement that can be captured with a 16-bit constant, right? So I can't jump really very far. If I do want to jump really very far, then I need to first do some preliminary calculations and put my jump address into a register, right? So let's say I put it into a register $T3, and then once I've done that, I can do jump register $T3. If I'm doing a straight jump instruction which says, I need to jump to this address, note that that particular instruction only allows me to put a 26-bit constant value. So if my jump location cannot be captured by this 26-bit constant, then like before, I need to figure out my jump address, place it in a register, and then use jump register. Now let's talk about endian-ness. Endian-ness refers to how a register finally gets placed in memory. So if you're reading a value from memory, okay, let's say you're getting something from memory location 400. Okay, so this is memory location 400. This is memory location 401, 402, 403, right? So low address is here, high address is here. Now, once I bring in a word, right, I've brought in this 32-bit entity. The question is, how do I place this into the register? If this first byte that I've fetched goes into the least significant byte of the register, that is referred to as a little endian register or a little endian architecture. And the x86 architecture is an example of a little endian architecture. And then once I've placed 45 here, the next byte 7b goes over here, the next byte goes here, and so on. I could also do the exact opposite, where the first byte I fetch from memory gets placed in the most significant byte of that register, then the next byte I fetch goes in the next byte, and so on, until the last byte that I fetch goes into the least significant byte of the register. So this is a big endian architecture, and is the one adopted by MIPS and adopted by IBM. So when you're working with your simulator, when you're working with your assembler and simulator, make sure that you pay attention to this and see how the contents of a register actually get laid out in memory, and confirm that it is indeed a big endian architecture. Now let me go through the different steps involved in compiling and executing a program. Okay, I'm going to take C as an example. So as a programmer, you first create a file, let's call it x.c. You might create multiple files, right? So there are other files, y.c, z.c, and so on. When you compile these programs, each file is individually compiled, and x.c gets converted into an assembly language file, that is x.s. Okay, so the compiler is essentially going to use pseudo instructions and labels and all of those things to produce an assembly language program that is, relatively readable for the programmer. Similarly, it also produces, y.s and z.s and so on. Now the assembler takes these assembly programs as input and produces an object file, in this case an x.o. And this object file essentially has the instructions in machine readable format, so it'll have a bunch of zeros and ones. It also converts pseudo instructions into multiple assembly instructions that are native to that architecture, that can be understood by that hardware. It also replaces labels with actual strings of zeros and ones that reflect that particular address, either a data address or a jump location. So once that is done, you have these object files for all of your different programs. You also have object files for various library routines that have been pre-compiled and saved aside for you. And the linker then takes over and stitches all these object files together. So in x.o, all the references that are known are basically resolved. So if you're referring to a data element, let's say p, then if p is defined inside the same file, then you figure out where p is, what is the address of p, and you replace p with a string of zeros and ones that refers to the address of p. But if you refer to some other data element, let's say q, which has not been defined in this file, then that unresolved reference is placed at the bottom of this object file saying, you referred to q, but I don't quite know where it is. Now it is the linker's job to find out where exactly q is placed, right? Q might be defined in this file in y.o, and so the linker figures that out, and when it stitches these programs together, it resolves all of these references. So this blank location for q gets replaced with the true address of q, which is determined by looking at object file y.o. And similarly, if you call a function, let's say printf, then that's a standard library routine. The linker takes the code for printf, makes it part of the larger executable program, and make sure that you're jumping to the right piece of code when you want to do printf. So the result of this linking operation is a single executable file that is referred to, at least in C, by default is referred to as a.out, and that has the entire code. That is a string of zeros and ones that refers to actual instructions that the underlying processor can interpret and execute. Once you produce these executable program, it needs to be loaded into memory before it can execute. So the loader takes care of that. It allocates memory, it places a.out in the right location, it initializes registers to the right value. It even links in dynamically linked libraries. So there are some library routines that are not statically compiled into a.out. The code for those routines changes frequently. So the loader at runtime says, okay, there are some library routines which are not part of a.out. So at runtime, I'm going to figure out exactly where those library routines are, make them part of the program, do the linking dynamically, and then it finally gets the program started once it is placed in memory, once the program counter is initialized. So that is ultimately how the program is finally executed.